Great, thank you.
Thank you.
Today I just wanted to take it a little bit more slowly and get through some of the proofs in the paper, as well as do some participation, because I think proofs, live proofs are way more fun when everyone kind of like, guesses the next step or what we can potentially do. And part of the other reason for that is because the solution to the problem I'll describe in a second that this paper proposes, I don't think is very novel or exciting. And I just think that like they set up a good theoretical framework and motivation for the solution that could inspire a lot of people to do more work in this space. And I think that's the important part. So I'll start off by describing the problem that we have. So the main theme that we're going to be talking about is disparate impact. And so I'll get into what exactly that is in a formal definition in a second. But we're going to be looking at disparate impact on graph data. And to solve this problem, the authors proposed the solution called fair adjacency, which is to empirically learn a fair adjacency matrix with proper graph structural constraints so that we can do link prediction in a more fair way while preserving predictive accuracy as much as possible. So now for what disparate impact actually is, we're going to be focusing on it in the context of dyadic relationships. And so dyadic relationships are any kind of entity that could relate two instances within our graph. And so in this case, the dyadic refers to a link. And we want to ensure that the rate at which we predict links is not affected by the rate at which they occur within a graph, dependent on a certain sensitive attribute. So an example of this might be when we have a news app that's collecting the political profile from a user in pursuit of like the user preference in news streaming, the system might only deliver app politics that the user is predisposed to agree with, right? So if we have, for example, a user node, this is in the case of a heterogeneous graph, but we'll be focusing on a homogeneous graph later. But if we have a user node and maybe so this is user one, this is user two, right now you've seen things with Twitter. If user one and user two and maybe user three here, they all have very similar political leanings, they'll most likely be recommended to connect with each other, right? So we'll have links going like this, but I'm sure there's also going to be it's going to be a very strong separate community elsewhere. And the links between there'll be links between these two users as well, maybe based on political preference. But if you ever want to recommend a user to connect with another person, it's likely that if a user 6 joins and they have like a very similar political leaning to user 4 and 5, they'll be recommended to connect with them as opposed to user 2, 3, or 1. So this link will most likely not be predicted by current message passing networks because of this disparate impact phenomenon, in which we tend to over predict that users will link with other users with similar attributes, and that kind of leads to problems like isolation of political leanings, and we don't want to end up putting people in bubbles. We want to make sure that we don't leverage any kind of exploitative information to like gender or politics or religion in order to recommend people to only to other folks within their community. We want to make sure that we recommend users to other users in a very fair way. So I was just wondering, do any of you have any other examples you can think of disparate impact within the graph setting, and especially within link prediction? Like it can be a very concrete example. As I just gave the example of maybe Twitter and politics, but any other ideas that people have?
Arjun, I want to clarify the question here. Do you mean that like user 3 and user 6 are connected, but they do not share the same label?
Right. So that's a good question. So all these users kind of have you're able to extract some kind of political information about all these users. But if let's say we're on Twitter, we don't want people to form very politically homogenous communities. However, if we're able to extract this political information, we'll only be recommending conservative users to other conservative users, as well as maybe only liberal users to other liberal users. So the diagram I was drawing here is to show that if let's say user 4 and user 5 may identify as more liberal, and user 6 has some sensitive attribute that might disclose that they are also have liberal political leanings, they'll be much more likely to be predict like a link between them and user 4 and 5, and no link between them and user 3 who might be more conservative. Right. So that's a really good example. So Alex put in the chat, when you have YouTube video recommendations, you might, let's say you have a more you have a more heterogeneous graph, and there are nodes that represent users, there are nodes that represent videos. You might have a similar phenomenon where you might have users being recommended increasingly videos that align with their political leanings. And it also creates this bubble effect. Yeah, so the main idea here is that there are certain sensitive attributes which we don't want to influence these like critical link prediction tasks. For example, like again, if we don't want to have political leanings be amplified or have this bubble effect created within social media, we want to be able to perform link prediction without taking this into account. We would want user 6 to communicate with user 3 and kind of get on common political ground. And the main objective here, in a very conceptual sense, before we get into like the actual definition itself, is this dyadic fairness that I previously mentioned. What we hope is that link predictions, are statistically independent of the sensitive attributes from the given two vertices. And in this case, we're focusing on graph neural networks, and the idea that inspired all of this work is this concept of demographic parity, which is a very critical measure within group fairness, which was first proposed by Cynthia Dwork. And the demographic parity measure essentially says that the probability of the classifier output, so in this case, the graph neural network output or link prediction output, given any sensitive attribute, should just be equal to the probability of the classifier output. So there shouldn't be a shift in this distribution. You want the conditional probability distribution to be very, very close to the probability of just the classifier output, that distribution. Okay. So I just quickly wanted to talk about some of the existing work in the space before we jump in to the proofs. So fairness in graph structure data is actually very relatively, it's not relatively like very minimally explored. And this has been a very big thing in computer vision and natural language processing. A very common example or very famous disparate impact study in computer vision was the gender shades paper that Timnit Jibru and Joy Bolamwini had released, in which they found that the ability of automated gender recognition systems when looking at pictures of individuals that were released by corporations like Microsoft, by Google, IBM, they all performed much more poorly for Black women than they did for either white women or Black men. So they were looking at intersectional demographics there, and they found that the ability of any of these systems to predict gender for a Black woman was about the same, that had the same accuracy as a coin flip. It was about 50%, which is really bad, as opposed to for a white man, which was around like 97% accuracy. And so again, this is an example of disparate impact. If we don't see a lot of examples of Black women in our training data set, we're much less likely to predict that a new instance is a Black woman. The machine learning system is not able to, it doesn't account for these disparities in our sample. And it's a similar thing for the link prediction task as well. If we don't see a lot of links between liberal and conservative users, we would be much less likely to suggest that these two users connect, because we'd be more likely to say that they should connect with other individuals with the same political leanings. So the couple of works in the graph space, they include Fair Walk. And so Fair Walk was a random walk-based graph embedding method that essentially revises the transition probability according to the vertex's sensitive attributes. So this is kind of one of those shallow embedding methods where you're learning the embedding for a node by doing a random walk that's influenced by the sensitive attributes of each node. There's also some other ideas like adversarially removing sensitive attributes from nodes, essentially predicting an output and then seeing, can you reverse engineer the sensitive attributes from the output? And so in an adversarial way, you can have the generator fool the discriminator, and that way you can learn like these representations of the nodes that don't encode information about the sensitive attributes. And the work that this proposes is because all these other things that I mentioned have been on the nodes themselves. We're trying to just figure out, are there any impacts? How do I mitigate bias within node representation so that I can perform more fairly on node classification tasks? There haven't been a lot of works that discuss the effect of encoded biases in node representations for the problem of link prediction. And so again, that's what this work addresses. And that's why I thought it was very cool. They also have a very interesting theoretical motivation for the solution that they propose, which I'll start walking through right now. I guess before I jump into the proof, are there any questions at all? Like, feel free to ask any questions about like what exactly the motivation is.
Question, right? It's clarification question. So music fairness is the objective to make the prediction statistically independent of the, let's say we just have one sensitive variable, gender, right? And then make the prediction independent of gender, right? Or you want to accomplish that independent of the gender, the prediction accuracy is about the same. Like the prediction accuracy for male and female about the same. So that's one objective. Another objective is that the prediction is really independent of gender, right? When you calculate the statistical dependency, they're different, but they are two different goals. Which one is the one that the paper is trying to accomplish here?
Yeah, so the one that the paper is trying to accomplish is the one that I mentioned earlier, the statistical independence between the prediction and the sensitive attribute. So the prediction should not be dependent on the sensitive attribute. So like the probability of the probability of predicting a certain output.
Okay, I see. So, which means that it's okay that if the prediction accuracy for, let's say, for female is very poor, where the prediction for male is correct. That's okay as long as the prediction is independent of gender.
Yes, that's correct.
Okay.
Yeah, so as you can see, there's a lot of different definitions, and they're all very they can be flawed. So I can quickly talk about, this is a little bit of a tangent, but there are multiple definitions of fairness that have been proposed. So this one goes under the name of independence.
Mhm.
Sorry, 1 second. My pen just really quickly died. Yeah, there's multiple definitions of fairness. So there's independence, in which which is the one I have on the screen right now. There's also this thing called separation, which controls for the actual frequency with which the ground truth label occurs. So you might have something like you essentially say that the probability of the prediction output and the sensitive attribute, they're both conditionally independent given the ground truth labels. And that would be that would encompass the idea of making sure that the predictions are actually more balanced, that they're more fair,
Mhm.
as opposed to like this, right, where you said, the accuracy can be really, really terrible for women compared to men. But as long as this criterion is satisfied, we call it fair. So the other one actually takes into account the frequency with
Right.
which the ground truth
Mhm.
labels occur. So this is independence, and it also goes by the name demographic parity. Both of them are the same thing. There's separation, in which the probability of C given A y is going to be equal to the probability of C given y, where C is the prediction, the random variable representing the prediction of the classifier, A is the sensitive attribute, and y is the random variable representing the ground truth labels corresponding to each of the examples in our sample. And then we have this last measure, which is sufficiency, which is kind of the reverse. So yeah, the probability of y given C comma A is equal to the probability of y given C. So all of these fairness measures are different, and they all kind of tell you different information about like what your model is doing. Importantly, they're all mutually exclusive. So none of these three can be satisfied like simultaneously.
Interesting. So previously I thought C is Y, but then it becomes this Y. So what is C again?
Yeah, so C is the prediction of the classifier, the random variable representing the prediction of the classifier. And Y is the actual ground truth label.
Y is ground truth.
Yes.
Okay, so now let's consider a situation. Suppose C is income and A is like education level, right?
Mhm.
And we know that C is highly correlated with this A. So then how we can make the first independence assumption true, right? We know that if we remove that education level, then somehow we cannot predict C correctly.
Yeah, so that would be more of like a design decision. So these are all criteria. These is just a general framework for criteria that you might want to set. Like maybe you want to use education level as a predictor for income, because you think that's a fair protected variable to integrate. But a lot of times, a better example might be like the prediction of income given like maybe like zip code, because zip code is very correlated with race in the US, and you don't want to have a model that has like high correlations with race. So in that case, you would want to satisfy this criterion of the probability of your model predicting some income given the zip code. It should be equal to the probability of your model predicting the income across the country.
Yeah, then I think this fairness problem is very different from the traditional problem, including, for example, lots of problems in social science and in economics. They want to find that A, right? So they want to know what kind of factors are important to the C. And then probably then we can find some solutions to address this issue, which is important to like policy making also. But here somehow it's like, if it's like sensitive for some certain A, for example, race, gender, age, right? If they're sensitive, then I want to somehow hide those information. But I'm not sure, like philosophical wise, whether it's a reasonable way to do that. Should we identify the issue and solve the problem, or should we just hide the problem?
Yeah, so the question you're raising is something that So I'm part of like a lot of these radical AI communities, and I've participated in some of these discussions around like, are we gonna radicalize the way that we like apply machine learning, or are we going to be more fair? Like, it's a very tough conversation. I think this delves more into philosophy. Like, should we should we be erasing certain information in the in the hopes that it actually is completely not encoded in our representations, and then hope that downstream that it doesn't have any detrimental impact on marginalized communities? Uh, However, like, we could also just not apply certain things like facial recognition to marginalized communities, because we know that it doesn't perform well, and it's very difficult for it to perform equitably for everyone. So it's like a very tough. Uh, it's a question that you would probably have to, like, you probably spend hours of discussion on to answer something like that. Like, how could this influence policy? Like, should we trust these systems if they satisfy these criteria to actually perform well for everyone?
I see.
Yeah,
Yeah.
I don't know how to answer your question. It's just like a very it's a pretty open-ended question,
Mm-hmm.
and it's something that we need to discuss, I think, as a community. Like, who are we impacting, and can these satisfying any of these criteria actually reduce that impact, this detrimental impact? Okay, so in that case, are there any other questions right now? Otherwise, I'm going to start going into the proof itself.
So what are we going to prove here with the theorem?
Yes, I'll state the theorem in just as soon as I set some of the preliminaries up.
Okay, great.
Okay, so I hope that's kind of like a more solid understanding of like the different notions of fairness and what exactly we're trying to achieve with this in this context with the independent / demographic parity notion of fairness. So the preliminaries, we have some graph G, which is a tuple of vertices and edges, and we're going to say that the vertices are represented by some vertex features, which we're going to denote by the variable x, which are an element in the set of n by n real valued matrices. Then we're going to have a non-negative adjacency matrix as well that describes relationships between every pair of vertices. And of course, this is an n by n matrix. And inside this matrix, the entry A sub UV represents the weight on the link that is bridging U and V. So for this edge U comma V, AUV is the weight associated with that edge. Every vertex holds a sensitive attribute. So we're going to use this function S, which takes as input a vertex, and it's going to return the sensitive attribute associated with that vertex. Furthermore, we're going to let gamma V be the neighborhood. So this is very common notation with all the GNN papers. It's going to be our one-hop neighborhood of V. And now this is getting into the problem-specific notation. So we have two different terms here. We have intra, and intra is going to refer to any edges such that SV is equal to SU, right? And so going back up to this definition, SV is a function that returns the sensitive attribute of a vertex. And so if we have two nodes that have the same sensitive attribute, we're going to call that like the link between them, we're going to call that an intralink. And similarly, we have a definition for interlinks, which are when SV does not equal SU. So this is a link between two nodes that do not share the same sensitive attribute. Yes, we're halfway through the notation. We're going to get into the statement very soon. So S is going to denote the cardinality of a group S, right? So if we have some kind of cardinality of Si, this is going to be equal to number of nodes for which for all n in V, Sn is going to be equal to Si. So we're just getting the number of nodes that all have that same sensitive attribute. And in our
So
case,
Arjun, I think I lost my track on the notes again. So what is S again?
all right, sorry, my writing is very big. So S is, maybe this is easier if I kind of zoom in a little bit, or sorry, zoom out. S is a function that you input the node and it gives you the sensitive attribute for that node.
You mean the attribute value?
Yes, the attribute value.
I see.
Right, so in our case, we're going to be considering a binary sensitive attribute. So it'll be something in the set 0, 1. So S could take a vertex and say this has sensitive attribute 0, or it has sensitive attribute 1.
Okay. Then for the inter and inter, what does that mean? Is defined over links?
Yes, it's a function that takes in a link UV and it tells you, is the sensitive attribute of U the same as the sensitive attribute of V?
So essentially to see whether the attribute value agree with each other on a certain link.
Exactly.
So why do they call it inter and inter? Intra-class and interclass, is that?
Yeah, so the intra is like, if you treat U and V as belonging to the same sensitive attribute class, then the edge between them is intra because the edge connects two vertices of the same sensitive attribute.
Oh, I see.
Whereas
it's kind of like a block model, right? So you rearrange your nodes according to the attribute value. So then you can have two blocks. And within each block, it's called interlink. If the link is cross blocks, then it's called interlinks.
Yes, I'm like 100% sure that they actually probably got their that like vocabulary from the block model like paper and all the other like literature surrounding that, because I think like the idea is that a lot of these nodes that share the same sensitive attribute form communities within your graph, and so you can almost think of it as each group of nodes sharing the same sensitive attribute belonging to the same block. And then, then the intra and inter vocabulary will follow from that.
Okay. So then what does this S sub I mean? I means the value?
Yes. So S sub I is, oops, actually there's a little issue here. So S sub I is the cardinality of all the nodes that share the same sensitive attribute. So it's a number of nodes for which when you plug in this node into that S function, it returns the I sensitive attribute. Just whatever I represents. So you might have S0 and S1. And so S0 would be the set of all nodes that have sensitive attribute 0. S1 would be the set of all the nodes that have sensitive attribute 1. And then we're just taking the cardinality of these sets.
I see. Yeah. So I think if we can visualize in a block model, then probably it's much easier. At least for me personally, I think it's much easier to understand.
So, for example, if we consider gender, right? Like, is gender itself an attribute here, or is like female is an attribute and male is another attribute?
Okay. Yes. So in this case, let's take that male female binary sensitive attribute. So the first answer to your second question is both of them would belong to the same. They're both different values of the same sensitive attribute.
It's the same attribute, but let's see if I have all my nodes, right? All of them have like this gender attribute, right? But then all of them, everything would be in my graph would be intra, all the links. Oh no, so they're treating as two different attributes.
Yes. So it's
Oh, okay.
maybe I can draw a quick diagram like Professor Sun suggests. I think it might clear some things up. So if we have here, like let's say we have a 3-node graph, and let's say that this node here and this node here, they both identify as female. And so we're going to assign them a label, we're going to assign them sensitive attribute value of 0. And then this one is going to have a sensitive attribute of 1 because this node identifies as male. So if I were to draw this dotted edge would represent an interlink, and this solid link would be an interlink.
So
So the first one is intra because both.
okay. So does this model assume that you only have this one variable, right? You consider like gender, right? You consider sensitive, right? So if somebody say, well, I have both gender and age, right? Then this model doesn't work on that, right?
Yes, it's only for one kind of sensitive attribute, at least that we're handling right now.
Okay, and that need to be a binary variable, like male, female. If you have a more than 2 choice, this does not work either, right? Or it's works.
So it still should work with more than one variable. With the variable has more than one possible value, it should still work. Like it can't do what you mentioned earlier, which was compositional fairness constraints. When you compose different sensitive attributes together and try to debias for those combination of sensitive attributes like race and gender. However, if you're only dealing with gender, let's say we have like k different genders that we're considering, then anytime 2 nodes have the same gender, that's an intralink between them. Anytime they're different genders, it's an interlink.
Well,
So
if you can, yeah, if the model can take more than 2 values there, right? Then even if there is like both age and gender, then you just treat the combination of them as different S, right? Then it should work, right?
Yes, it should work. So if you were to do that, you can obviously do like a composition. You can treat like black woman as one kind of sensitive attribute. Essentially, it would grow. The number of different combinations would be the cardinality of how many sensitive attributes there are, like how many values each sensitive attribute can take on. So you just multiply all of them together, and you can do that.
Okay.
However, like I don't know how. If you're trying to do that at like a large scale, I think the question becomes how efficient is that to control for so many different combinations of values that this could take on. Okay, so we're going to define one more set, which is going to be S0 tilde. And S0 tilde is going to, I think that's too small. S0 tilde is going to be the set of all vertices in S0 such that the neighborhood of V within the intersection of S1 is not the empty set. And so what exactly does this mean? Conceptually, all this means is that S0 tilde is the set of all nodes in the group S0 that are on the boundary.
Hello?
Right? So like maybe in this 3-node graph that I just drew above, this node here is going to be in S0 tilde because it's on the boundary between all the 1 labeled nodes and all the 0 labeled nodes. However, this node here will not be in S tilde because it doesn't have any connection to 1 labeled nodes. And then we're also going to have a uniform distribution U. That's going to be, it's a discrete uniform distribution over all the vertices V. And finally, we're going to have a link prediction function. And this link prediction function is going to map products of vectors to a single value. So it's just a quadratic form. What it does is it takes in representation of one node, a representation of another node, and it's going to multiply the representation times a matrix times the other representation and give you a similarity score that will determine how likely is there to be a link between those two nodes. So the general purpose, again, to reiterate, of dyadic fairness is to predict links independently of whether two vertices have the same sensitive attribute or not. So predict. So the goal here is to predict links independently of if they have the same sensitive attribute. And in a binary classification problem, demographic parity would expect the classifier to give positive outcomes to two sensitive groups at the same rate. So we're going to turn the two groups from demographic parity into the groups of intra and interlinks. So intra and interlinks will now be our two groups for which we want to predict positive outcomes at the same rate. And in the case of binary classification, right? Because like if two groups have positive outcomes at the same rate, they're also going to have negative outcomes at the same rate because it is binary classification. So with vertices, so let's say we have some vertex representations V and U. Formally, we would satisfy dyadic fairness if we have the probability of G of U and V given SU equals SV. And so again, as a reminder, G is our link prediction function that takes in the representations of two vertices and gives you the similarity score, the probability that there's a link between them. So this is just the first part of the definition, and there's a second part. So given this idea of predicting links independently of if they have the same sensitive attribute and predicting inter and intra links at the same rate, does anyone want to try filling in the rest of the definition?
That would be the G given the SU is not the same as SU, right?
Yeah, perfect.
So
So it's G. Sorry, go ahead.
I'm just trying to think, like, let's see if in the case where when they're not the same, right? This interlink, right? Let's see, in the extreme case when there's no interlink, okay, very few interlink, all the links are intralink, right? And then this model still encourage these two probability to be the same.
Yes.
Then at the price of actually the prediction accuracy going to be low.
Yes.
Okay.
So the again, this kind of goes back to the idea of like a design decision. So if you as the designer of your system just adamantly do not want a certain attribute to influence the predictions, regardless of how correlated or how causal that attribute might be of what you're trying to predict downstream, you would still want this to be the case. Okay. So this is the definition that we're going to be working with. And one of the most interesting things to me, like I think this is the coolest result that this paper had, was that the demonstrating demographic parity in the outcomes of link prediction can be sufficiently reduced to the achievement of fair vertex representations. So actually what this is saying is that if we can learn fair vertex representations, that's a sufficient condition for this dyadic fairness criterion. And so we'll kind of figure out exactly, I'll state in a second what exactly it means for vertex representations to be fair. But the big idea is that fair vertex representations can be a sufficient condition for fair link prediction, at least according to this definition. And so the way they do this is they reveal how the pipeline of a one-layer graph neural network can affect this demographic parity. And we are going to draw the conclusion that for an arbitrary graph, using GNNs for the embedding, properly regulating the weights on the existing graph connections can actually contribute to fairness as well. So let's start diving into our first theorem, actually the proposition which is a proof of this, that fair vertex representations imply fair link prediction. Okay, so this is proposition 4.1. And it says that given our link prediction function, let's take a very specific case of our link prediction function, which is, it looks something like this. So it's going to be V transpose times sigma times U. So V and U are the vertex representations. And sigma is going to be a positive definite matrix. Now we're going to add some more assumptions here. We're going to say there exists a Q greater than 0, such that for all the vertices that we have in our graph, the norm of the representation for that vertex is going to be less than or equal, the L2 norm is going to be less than or equal to Q. So we're essentially saying here that the norms of all the vertex representations are bounded. Furthermore, we're going to say that the expectation of all our nodes is going to be a real valued vector that's m-dimensional. And now the first part of this conditional statement says the expectation of the vertex of all the vertices in group S0 minus the expectation of all the vertices in group S1 if the L2 norm of the difference in expectations across these two groups is less than or equal to some delta, then we can show that this implies that our demographic parity is going to be less than or equal to Q times the norm of our matrix that's used in our link prediction function times the same delta. And so you might be wondering, what exactly is demographic parity? Like, how are we defining it here? So this demographic parity is going to be the expectation of GVU given SV is equal to SU minus the expectation of GVU given SV does not equal SU, and the absolute value of this. Okay, so just to conceptually explain, what's going on here, we're saying that if the average representation is different, if an average representation for the first sensitive attribute, all the nodes represented by the first sensitive attribute, the difference between that and the other value of the sensitive attribute, if that difference is bounded by some value delta, then we can also bound the demographic parity between all the nodes in our graph. Because I guess I understand that this can be a little bit confusing. So I was wondering if anyone has questions about notation or just questions in general here before I move on.
Before going to the proof, so I just have some another motivation example. Pearl can explain why this is important. I want to follow your example, right? So political polarity example. So if suppose in Twitter, we just based on whatever information we have collected to recommend friends, then most likely, right, according to your example, then you're going to recommend people who are left-leaning to left-leaning people. Then it will form this kind of echo chamber, right? So it's then we're going to have two communities. Then if you visualize that, so essentially we're going to have two very polarized communities. So this is what we don't want to see, right? So then how we can avoid this? It's for link formation, there are all kinds of reasons, and this kind of underlying this kind of political preference definitely is one of those possible factors. But somehow if we want to alleviate the phenomena of this polarity, polarization, right? So we wish that later on, when we try to recommend friends to you, we don't want to base on that political polarity information. So in this case, we wish that if we utilize that political polarity information or political preference information, even we use that, then the prediction result is as if we don't use that information, right? So I think from this perspective, I can kind of feel the value of this work. Otherwise, if so this is my personal interpretation why this is important, PC given A equals to PC is important for this particular application. But it's not the case for all the applications. So, but anyway, so I think at least I think I'm partially convinced that we need to do this type of research.
Yeah, that's a very good example, and you're very right that it's definitely not the only criterion that matters. Sometimes you want to take more into account than just whether it's as if you didn't have the sensitive attribute at all. There are a lot of cases where you want to maybe reduce the impact that a sensitive attribute has on the outcome, or even look at proxies or other kind of information that could give away similar highly correlated variables that could give away similar information with regards to the prediction or the downstream task. Yeah, there's it's a very highly dimensional problem in so many ways, and I think this is, like you said, this is one very specific way and very specific case of making something more fair.
Right. So, but the problem I just mentioned, right? It's hard to say whether it's a fairness problem, because somehow, for example, political polarity or polarized kind of political preference, whether it's a fairness issue or it's a different issue, right? But at least we know that at some time we really wish that we can, for example, recommend people who are more diverse, Okay, so your friends should be more diverse. So that's why we wanted to kind of hide some information during this process. And then when we say hide some information, as you point out, right? So it doesn't mean that as simple as we just remove that attribute in the prediction model, then it's done. Because there could be many other features which is correlated with that hided, the feature to be hide. So that's why we also need to take that into consideration. So that's why this kind of more rigorous model makes more sense.
Yes, yeah. I think like there's also other good examples of which, so a lot of the definitions that I brought up are from Barocas and Hart's NeurIPS 2017 presentation, where they brought up the use case of recommending ads to users. So they found that if like a lot of software engineering ads were not recommended to women because they found this correlation that fewer women were applying to software engineering positions, which is obviously the result of systemic issues and sexism within tech. However, like we want to make sure that you don't consider gender when you're recommending ads, because that's very pivotal. Like you want everyone to have equal opportunity to go pursue such a job.
This is also a very good example. Yeah, I'm not sure whether later you are going to mention the connection to causality, but anyhow, I think some probably you also have thought along this direction. Maybe in the end also, you probably can also comment.
Okay, I can do that for sure. Okay. So we're going to get into the proof of this now. And the proof is basically we're going to start off by simplifying some of this notation. So we're going to let P be equal to the expectation of all the vertices in S0. And we're also now going to let Q be equal to the expectation of all the vertices in S1. And we're going to look at the expectation of the intras minus the expectation of the interlinks. And so you'll notice that this absolute value of the difference in expectation of all the intra and interlinks is just the same thing as our demographic parity measure up here, right? We're looking at the expectation of this link prediction score, given that two vertices are, given that the incident vertices for an edge share the same sensitive attribute. How different is that from when the two incident vertices don't share the same sensitive attribute? So we're going to expand this a little bit. We know that this is going to be equal to the expectation of B transpose sigma U given V is in S0 and U is in S1. So this is going to be all our intra links, right? So this component is the intra, the sensitive attributes are different. And then we now have to consider the expectation. We subtract V transpose sigma U. V transpose sigma U of, given that V is in S0 and U is in S0, or V is in S1 and U is in S1. So now we can look at the definitions here, and we see that the expectation, the first expectation term here, because this is a, by linearity of expectation, we can say that this is just equal to the absolute value of P transpose sigma Q. Remember, P is the expectation of.
For the intra, why do we only consider one direction from S0 to S1, how about the other direction?
Right. So this is the V and U are just dummy variables. Like you can assume that V and U change places at some point in the set. So like you can have V take this accounts for both directions. So like V could be in S0, and if you fix V to be in S0 and U to be in S1 at some other point in our set, the same vertices will be swapped. And so you'll have the other direction as well. Sorry, did that help, or is this
I think because the distribution would be the same, right? So if there's a link from S0 to S1, there's also a link from S1 to S0. So expectation-wise, they're the same. So they only need to consider kind of one direction.
That also is a valid explanation. Like either way, you're either adding you're duplicating the number of terms in the sum for the expectation, or you can just that there's going to be a symmetric core.
Right.
So either way, it'll come out to the same value of E transpose sigma U. Like the expectation will be the same regardless.
Okay.
So we have P transpose sigma Q, and now we're going to use the conditional expectation theorem. So we know that the number of possible intra links within, sorry, this should be inter, but the number of possible intra links within S0 is going to be equal to this, because the cardinalities represent how many nodes we have, and there's going to be any graph with n nodes has potential to have n squared edges between all of them. So we're just looking at what's the possibility of there being an intralink in S0 over the probability of the total number of possible intralinks in S0 and S1. So we're going to take this probability that there is an intralink in S0 and compute the similarity. And then we're also going to take the probability that there's an intralink in S1. And once again, compute the similarity. And now we're just going to do some factoring.
So why the expectation of the inter can be reduced into P transpose sigma and Q? P, what is P?
Yeah, so,
is that expectation? Oh, okay.
Yes, it's expectation involved. Yes, so just like by linearity of expectation, you can get the expectation of P and Q, and that's all this is here.
Yeah, I think I didn't do a good job in tracking all those notations, but yeah, I think it's good.
So we can factor this here as a product. So we have Q minus P transpose times S0 squared over S0 squared plus S1 squared sigma P plus S1 squared divided by S0 squared plus S1 squared sigma Q. And so, yeah, you can also check that this factorization holds, but this is what this is an equivalent form. So now to further simplify notation, we're going to let alpha equal S0 squared over S0 squared plus S1 squared. And we're going to let beta equal this term above. So we can now we're just going to rewrite this. We're going to say this is equal to Q minus P transpose times alpha sigma P plus beta sigma Q. So now we're looking to bound this absolute value. So can anyone think of a next good step for bounding such an absolute value, like a very famous inequality that we could use? Any takers?
Just to separate the two. I didn't know the name of that inequality.
Yes, yeah, that's the right
Mm.
one. So it's the Cauchy-Schwarz inequality. We'll just separate the two into a product of norms. So this is what you had meant, right? Like something like this.
Yes.
Sorry, 1 second. This should be a minus. Yes, so that's exactly right. We're going to have to separate it into a product of norms. And then we're going to further reduce this. So does anyone recognize what the norm of Q minus P is? I know there's so much notation here, but we said up here that Q minus P, by assumption, the differences norm is going to be less than or equal to delta. So we can bound this term by delta. And we can also factor out the norm of sigma. And now we're left with something that looks like this. We can write this. Does anyone want to explain how we can write something like that? Or have any thoughts about it?
It's a triangle inequality.
Yes, exactly. So it's just the triangle inequality. So just a quick side note here. If we have something that looks like this, we know that this is going to be less than or equal to A plus negative B. Oops, sorry, this should just be equal. But then the next step is going to be less than or equal to A plus B. And that's a triangle inequality that result that let us get to this step here. Okay, and finally, we can take the fact that we know that all the vectors, we mentioned earlier that all of these vectors, the representation is going to be bounded by some constant Q. So let's look at the expectation. Let's look at the norm of the expectation of V. We know that this is going to be less than or equal to the expectation of the norm by linearity of expectation. And we know that this V2 is less than or equal to Q, which means that the expectation of this is going to be less than or equal to Q. Therefore, we can bound both P is less than or equal to Q, and we can also say the norm of this other average is going to be less than or equal to Q. So ultimately, what this gives us is that we have delta times the norm of sigma times alpha Q plus beta q. And there's one last simplification step here, if anyone can remember the notation and point it out.
Beta equals to 1 minus alpha.
Yes, perfect. So alpha and beta, they sum up to 1. And so all we have to do now is just say that this is going to be, this is just going to be equal to q sigma norm delta. And this completes the proof. All right, so as just to reiterate, what this shows is that if we have this bound on how different the average of node representations across two different sensitive groups is, that implies the demographic parity for link prediction is also going to be bounded by this amount. And this is a really good motivation to show that if we can learn vertex representations that don't differ by too much across different sensitive groups, then we have a good chance of achieving demographic parity. Now you'll notice that this is a sufficient condition, right? So it's not a necessary condition. So we'll see in a second why you can actually have fair vertex representations, but it still might not improve the demographic parity of link prediction.
I have a question on the sigma. So it says like GVU can be decomposed into this one, which seems to me is like kind of SVD decomposition. Is that the case? So sigma is it like a diagonal matrix?
So sigma is just any positive definite matrix that's used in the link prediction function. It's used like this. We have this definition here that the link prediction function is going to involve this positive definite matrix sigma. In most cases, we probably use identity matrix, but it can be any positive definite matrix here.
Okay.
So why is sigma PSD? Is that a requirement we set or?
Yes, so it's positive definite just because of, actually, I can't really say right now where this comes into, oh, it's just because they want the link prediction score to always be greater than 0. I'm not sure why exactly they didn't say allow for positive semi-definite as of now.
But sigma is something we pick rather than something we learn. Is that the case?
It can be either one. So it can be a learned matrix, or it can be just it can be like a matrix that's handcrafted. But the idea is that when we're doing this proof, it's going to be fixed.
But if we learn it, we're going to have this additional constraint saying that this parameter matrix needs to be PSD.
Yes.
Okay.
Yes, I know that, like, in most cases it's not a requirement, right? Because you might do something like you don't set that constraint, and then you might apply a sigmoid afterwards in order to push it between 0 and 1. But in this case, for the purpose of their proof, they assumed it was positive definite.
Okay, thank you.
Okay, so now we're going to move into the GNN section. And just some background on the GNN stuff. We have a GNN parameterized by theta, which takes as input our node features and some kind of normalized adjacency matrix. And this is going to be equal to rho times this normalized adjacency matrix times the node features times some learned parameters W. And as most of you know, like this multiplication between the normalized adjacency and node features, that is our neighborhood aggregation step. And then we also have our feature embedding phase, which is when we multiply by this learn parameter. So this neighborhood aggregation or vertex feature smoothing or whatever you'd like to call it, that's the first step. We can think of this as kind of like a first step. And then we can also do our embedding phase afterwards. Or, like, I mean, the great thing about matrix multiplication is that it's associative. So you can do the embedding first and then neighborhood aggregation, or vice versa. It won't make a difference. But in the case of this paper, we're doing aggregation first and then the embedding step. And the analysis can be carried out for other normalizations. But in our case, we're going to look at the normalization in which this A tilde is equal to the degree normalized adjacency, so like the random walk matrix. And kind of breaking down what exactly this does. All we're saying is for, at the node level, the aggregation for a vertex V is going to look like the degree of V inverse times the sum of all of the neighbors. And so I want to emphasize here that both the degree and the summing is it's a weighted combination. So it takes into account the weights within the adjacency matrix, because we didn't assume like a binary adjacency matrix. We assumed anything with like positive real values. So yeah, like here, or sorry, non-negative real values. So this is the entry, the V youth entry, the weight corresponding to the link between V and U in our adjacency matrix, and this degree is also weighted. So it's just the sum of the weights on all the outgoing links within our graph. Okay, so now we're going to do some abbreviation. We're going to say that mu naught is equal to the expectation of V of all the V's within S0. We're going to say mu1 is equal to the expectation of all the V's in S1. And we're also going to let sigma denote the maximum deviation of the vertex representations. So namely, what sigma represents is for all V in S0, we have that V minus mu naught, and we're taking the infinity norm here, is going to be less than or equal to sigma. So for any entry in V versus like the average value, so mu naught across all the vertices that are in S0, the maximum deviation within any entry is going to be less than or equal to sigma. And for all V we're going to have the same property for all V in S1. Sorry, it's just so much notation, but there's some more notation here. The maximum degree we're going to set as the max, just basically what exactly it's whatever you'd expect. So it's like the maximum weighted degree for any node in our graph. And additionally, we're going to have this variable MW, which represents, actually, I'm just going to call it M. This variable M, which represents the sum of all the link weights that are like all the interlink weights. Okay, cool. A lot of notation. I'm going to state the theorem now for theorem 4.1. And then I think the proof of this one is a little bit more intuitive and straightforward, and so it won't be as confusing with the notation. So it's saying here for our graph with non-negative link weights, after conducting one mean aggregation over the graph, the consequent representation discrepancy between two sensitive groups. So this is our representation discrepancy here. This demographic parity measure after we've done one vertex smoothing / neighborhood aggregation, whatever you'd like to call it. Once we've done one of those, this is what our demographic parity is going to look like. This is going to be bounded by the max of, and I'll define a lot of these variables next. Alpha min mu0 minus mu1 infinity norm minus 2 sigma. So whichever one is larger, alpha min times the infinity norm minus 2 sigma or 0. So we just basically want to keep it positive. Wait, sorry, 1 second. This is the lower bound. It's going to be greater than or equal to this quantity, or, and it's going to be less than or equal to this quantity here. Okay, so the actual values maybe I won't define them just yet, because the first time I looked at this proof and I kind of was like going through all the calculations, like I was so lost by all the all the notation and everything. So maybe I'll walk through the proof quickly, and like what alpha max and alpha min are will be much more clear after that. Okay, so as we covered earlier, an aggregation around a vertex V in our graph neural network is going to look like this. 1 over the degree of V times the sum of all the neighboring representations. And the first thing we're going to do here is break this sum up into two different sums based on our sensitive groups. So we're going to write the sum as two separate sums. So we're going to look at the intersection of the neighborhood with S0. And we're also going to look at the intersection of this neighborhood with S1. And so every node belongs to either S0 or S1. And so if you were to break up, this is basically going to be like a disjoint set, and when the union is going to be omega. So like it'll be every single node in the graph. So this is a valid breakup of the sum. We want to now use a special kind of notation to make things a little bit less complex. So we're going to say that for any vector u, any representation of a node u, if it satisfies this property, it is in between mu minus sigma or mu plus sigma. So remember, mu is just some average, and then sigma is our deviation in the infinity norm. Then we're going to say that U is an element of this set. All the vectors that lie between these bounds. So now we can rewrite our aggregation using this notation to make things a little bit cleaner. So we can say the aggregation around a node V is going to be in the set of this vector here. So that was a lot of stuff there, but all we're doing is we're taking a linear combination of the means that we had previously defined. So mu naught is the average of all the vertex representations within, for all the nodes belonging to S0, and mu1 is the average of all the vertex representations for the nodes belonging to S1. So all we're doing here is we're taking our previous aggregation formula, and we're looking at how far would an aggregation of V differ from like the average across all the vertex representations. So we're writing it in this bracket format, which will give you some information about the deviation of any of these aggregations, with respect to the averages of the original vertex representations themselves. And so we're just doing this weighted sum here, this fraction times mu0, and then this fraction of the degree, this fraction of the link weights out of the total degree of the node times mu1, and we have this deviation here of sigma. And so now I can actually write this like this: mu naught plus Can anyone, if you're not too lost, can anyone give me like why I can do that? Why does this simplification work? Or also feel free to ask any questions that you have. I'm happy to go back and make sure that there's no confusions.
Arjun, can you move to earlier place, just maybe 1 or 2 lines? Yeah, okay. So what's this mu again? That's u, right? Is that an embedding vector?
So is it the u or the mu that you're talking about?
Yeah, I'm not sure. Yeah, I'm talking about u. Okay.
Yes, so this one here.
Yeah.
Yeah, so u is just, I'm just saying for all u that fit this description of being within some bound sigma from mu, we can say that they're an element of this set, mu plus or minus sigma.
So what's the semantic meaning of u here? It's not embedding, right?
Yes, it's a node embedding.
It's embedding. Okay, so it's a vector.
Yes.
Okay, it's a vector. So then why do we need to assume this vector is within a range?
Right, so this is kind of towards the assumptions that were made in the theorem itself. So we have in the theorem that,
That's our assumption, right?
yes, that's our assumption.
Okay, I see.
The assumption is that there is some sigma which will bound how far away each node embedding is from the mean of all node embeddings.
Okay.
Sigma.
Okay, so can you please move to the place that you stopped?
Okay, so the basically what's going on here when we do this rearrangement is that we know that degree of V is equal to this sum. So all the weights of all the links that are going to the S0 sensitive group, plus the weights of all the links that are going to the S1 sensitive group. So if we sum up all of those, we get the degree of our vertex V, which means that when we have this stuff up here, this term and this term, they sum up to 1. So we can actually re-express whatever's inside the brackets by basically saying 1 times mu0 plus this term intersection with S1, and then take the difference of the means here. Okay, any other questions before I continue? Okay, and like feel free to just interrupt at any point if you have questions, because it's like better that we understand what's going on as opposed to like me continuing ahead.
Is there any assumption about like how mu1 and mu0 should be differ?
That's a really good question. So I think the mu1 and mu0 differing is like a different part of the proof. So that was like the proposition we had done earlier. Like we had shown here that mu1 being not too different from mu0 by some amount delta can give you some implication of the demographic parity bound. And so we'll actually see in a corollary after this, while this itself doesn't take into account the disparity between mu0 and mu1, we can combine this theorem with the proposition to get a joint statement which does take into account the difference between mu0 and mu1.
Okay.
Okay, awesome. So here, let's see, we're going to let BV denote the sum of all the nodes in the neighborhood, and we're going to let S opposite be the group corresponding to the opposite sensitive attribute of V. And then the expectation of for S0 is going to be, so here we had shown that the aggregation for like all the V's, for all the V's, like basically aggregation across, both sensitive groups. But here, if we're only considering the expectation of the aggregation for the vertices within, the sensitive group S0, we can say that this expectation is going to be one over the number of nodes in S0 times the sum of all the nodes in S0 for these values. Right, so all we're doing here is we're taking the fraction of the nodes that happen to be within S0, and we're taking this previous sum that we computed here. For like any given node, we found that this is the expected value of its representation post aggregation. So now if we just want to find the expectation across all the vertices within S0, we just take a simple average over all the vertices in S0 for the same quantity. So mu0 and beta v is going to be equal to this fraction here. So we're just substituting this fraction with beta v in our term below. And this actually can you can actually move this mu naught outside. So we can say that mu naught plus 1 over S0 we don't want that anymore. We can just only focus on the BV inside here. And we have the same thing for S1. So for S1, it's going to be the exact same setup. It'll just look something like this. So the expectation of the post-aggregation representations of all the nodes in S1 will look like this. Just following the exact same steps as above, but for S1 instead. So now we have these two expectations here. So post aggregation, and we want to look at how different are they? How different are these two different expectations? So now that we've done the aggregation. So if we just simply subtract these two, so when I say these two, I mean this one here and this expectation here. If we just were to simply subtract them, we'd get that the difference is going to be equal to is going to be equal to 1 minus 1 over S0's cardinality plus 1 over S1 times mu0 minus mu1 plus or minus 2 sigma times 1. So again, all I'm doing here is I'm just subtracting these expectations. And if I have mu0 minus mu1 And I can basically pull that into this mu0 minus mu1 factor. So that's where this 1 comes from, simply subtracting the other two terms. And this 2 sigma comes from the fact that you might have, a deviation that's the maximum deviation in both directions. So just kind of like when you find the standard deviation of a difference in distributions, the deviation adds. And so that's where the 2 sigma comes from when we only had a sigma here. And now we're very close to like being able to bound this difference. In fact, all we really care about now is studying the range of this term alpha prime, which we're going to let stand in for 1 minus 1 over S naught V in S0 plus 1 over S1 V in S1. So first, we're going to consider the term, this term here. Can we bound that? And so the answer is, of course, yes, we can do something there. And we look at the sum. This is going to be equal to, as we defined above, beta v is equal to the fraction of the weights that are on interlinks over the total degree of a vertex. So for S0 itself, right, so this is only for the case of S0. For S0, we can say that this is equal to the sum, the neighborhood, when it intersects with S1 of the interweight links divided by the degree of V. And if you recall previously, we had defined a D max, which is like the maximal degree. So we can say that this is greater than or equal to, we can pull out this maximal degree. And now we have two sums. With the term being AVU. And we will recognize that AVU, this two sums here are basically just the sums of all the weights on interlinks, which we had also previously defined by M. So we can say that this is just equal to M over D max. So now we have a lower bound on this term, but now we want to find an upper bound on this term. So let's take a look at the degree of V. And we know that the degree of V is going to be equal to, I said up here, the degree of V is equal to this, right? Like we are looking at all the weights on outgoing links, and you can take, the sum of these, two different intersections, because S0 and S1, all nodes belong to either one of those two groups. But clearly, because all the link weights are positive, we can say that the degree of V is just greater than or equal to just all the neighbors that are in S1. We're just getting rid of all the neighbors that happen to be in S0. And so then going back to beta V, we see that beta V being this sum here, the weights of all the links that are inter over the total degree for the node V. Clearly, because this term is greater than or equal to this term, this beta V is going to be less than or equal to 1. And now we just want to sum up all the beta v's. And we see that the sum of all the beta v's is going to be equal to v in S0 tilde, which S0 tilde is all the nodes on the border. So all the nodes in S0 that have links with S1. And so we can say that these two are equal with beta v, because beta v is nothing but beta v requires that there's this intersection with, the opposite sensitive group. So if we don't even need to consider the links that are going to the same sensitive group, because that'll all be 0 in the context of beta v. So we only need to look at links going to the opposite sensitive group, which means we only need to consider nodes that are on the border of the two sensitive groups. And this is therefore going to be less than or equal to all the nodes on the border 1, because we show that each beta v is less than or equal to 1, which in turn will be less than or equal to the cardinality of all the nodes on the border. Sorry, this should just be equality. Okay, so we've now shown that that m over d max is a lower bound on the sum of all the beta v's, and that the cardinality of the number of nodes, so the set of all nodes at the border, is an upper bound on the sum of all the beta v's. And we can do the exact same analysis for S1. We've only done S0 so far, but it'll follow basically the exact same pattern, in which we'll see that it's going to look something like this. So all the nodes at the border in S1. And we'd wanted to show a bound on this term, alpha prime. And since we now have upper and lower bounds for the sums here for beta v, we can give upper and lower bounds on alpha prime. So namely, because there is this subtraction here, we would need to swap the bounds in order for them to hold for alpha prime. So essentially here we see that alpha prime is going to be somewhere in between 1 minus, right, so we have these divisors here, S0, S1. It's going to be 1 minus this this fraction plus this fraction. And on the other side, the upper bound of alpha prime is going to be based on the lower bound for the sum of all the beta v's. So it's going to look like this: 1 minus m over d max plus 1 over S1. And this bound on alpha prime, we now want to look at the bound on the absolute value of alpha prime, because this will give us some information about. So we had this difference here, but we want the information on the absolute value of the difference, because that's how we had defined demographic parity. So we're going to look at the absolute value of alpha prime, and we'll see that the upper bound on this absolute value of alpha prime is going to look like this. The max of 1 minus this is the same fractions that we had defined before. And similarly, we're going to have a situation for the minimum of this absolute value. And the minimum is just the same thing as this, except we're going to swap out the max with the min. So we're just taking, given these two that we have here, we have the lower and upper bounds on alpha prime, then the upper bound on alpha max is going to be the maximum of these two bounds, and the lower bound on alpha prime, on the absolute value of alpha prime, is going to be the minimum of these two bounds. And from here, we can see that we can give an upper bound on the entirety of this demographic parity measure post-aggregation. So namely, we can say that it's going to be equal, it's going to be bounded above by alpha max. Plus this error term here based on the sigma. So alpha max we previously defined, and the reason we were interested in that is because we wanted to look at this property here, but we still need to consider now this mu1 minus mu0 and also the deviation that could result from any kind of aggregation. So this mu0 minus mu1 makes sense because we're just taking the L2 norm, and this 2 root m sigma comes from taking the norm of 2 sigma times the all ones vector. So if we just take the norm here, we know that the all ones vector is an m-dimensional vector, so it's going to look like 2 root m sigma. And we're also now going to look at a lower bound on this demographic parity measure. So we now consider the ith entry of mu0 and mu1. And the ith entry is going, we ideally want this to take all non-zero values because demographic parity wouldn't make too much sense if it were negative. And so this non-zero probably should say positive values here. Or I guess non-negative values rather. So what this is going to look like is we want 1 minus 1 over S0 and we're looking at the ith entries of the mu0 and mu1 vectors. This is going to be greater than or equal to 2 sigma because of this deviation that we had mentioned above. Right, like this quantity in the difference should be greater than or equal to 2 sigma for all entries because we don't want this difference to take on non-negative values. So ultimately what that's going to entail is that the demographic parity measure post-aggregation is going to be lower bounded by whichever one is greater. Alpha min times mu0 minus mu1. Sorry, this should be an infinity norm because of these ith entries. minus 2 sigma or 0. And so this alpha min is just the quantity we calculated above. It's just the minimum of one of these two terms. And so that's how we obtain the upper and lower bounds on both of these.
So Arjun, I just want to have a gentleman reminder here. We only have 5 minutes left, but it seems like we haven't gone through the algorithm itself and also experimental results. But
right. So I mean, if it's okay, I think like I can talk about the algorithm at some point, but I don't think the algorithm was very like I don't think it's a great contribution in my opinion. I think like this proof was probably the more important part of everything.
I see. Yeah, it's very technical proof, very sound.
Yes. So in the last 5 minutes, I can wrap up like everything. Like it'll all make sense right now, I hope. There's just one last step in the corollary that will combine the last two results together. And it should make a lot of sense about how we can motivate future contributions. Okay, so just very quickly then, we want to now consider everything. We're going to put together the results of the proposition and the theorem. So recall that we have this GNN, which is going to be a nonlinear activation function applied to this normalized adjacency matrix times the node features times these learnable parameters. And so now we want to bound this demographic parity, and this is going to be after one layer. So what's the first thing we can do? We can look at that this is upper bounded from the early proposition here. From this proposition here, we can show that this is nothing but, this upper bound here is nothing but Q prime times the norm of sigma and the difference in the means, and the primes mean nothing more than just, this means post aggregation. And then if we have a Lipschitz constant for rho, our nonlinear activation function, we can further write this as Q L squared, where the Lipschitz constant for rho is L squared times norm of sigma, norm of the weight matrix squared times mu0 minus mu1 plus 2 root m sigma. So the reason for this is Q prime is going to be, when you plug in Q prime through the GNN, it's going to be bounded above by this. That's why we get one L from here. And then we get another L from applying the GNN to the norm of the difference of these means. And so ultimately it'll come out to this bound that looks like this. And what exactly can this tell us? We can see essentially here that there is a noticeable error term, but simultaneously we have this alpha, which kind of serves as a contraction coefficient. We can say that assuming that the vertex representations themselves are fair, with each layer of a graph neural network, assuming that this error term is not too high, we can reduce the demographic parity for link prediction between pairs of nodes. And so I don't have time to get into, since it's 4 p.m. now, I don't have time to get into there were some interesting examples at the end of the paper that I think you should check out for cases where this error term is so big that it matters. But in most cases, applying a GNN when the vertex representations are pretty similar can help reduce can help improve demographic parity for link prediction. Okay, I think that's all I have to say for this.
Thank you, Arjun. Yeah, it's a very interesting paper, and I think it provides like very new perspective in solving the problem of like fairness in graphs, right? So previously, I think I mentioned the Will Hamilton's paper, which is more from like empirical adversarial learning perspective and try to solve the problem. But here it's more like from they try to understand how the graph neural network can kind of propagate the error around. Right?
Yes, yeah, exactly. And I genuinely think that it's important going forward for everyone who's interested in this to like consider the graph structure, because the stuff with like debiasing, like adversarial debiasing, is that it's so tricky to get it to converge. And I don't think we even understand adversarial debiasing too much in the context of like theoretically in the context of other domains, so let alone graphs. I think there's so many cool things about graph structure that could be leveraged to improve fairness and make algorithms that are much simpler than adversarial debiasing that are more effective.
Okay. Now, one more comment. So because for graph neural network, it's kind of combining this feature propagation and this nonlinear transformation together in one layer. I think might be interest in itself just to try to see how this label propagation mechanism will kind of amplify or maybe other effect on this sort of error or bias. Yeah, in other words, it's not necessary that we start from the graph neural network, which is a more complicated operator.
Right. So like even like for the simple label propagation algorithm, because we don't have this assumption anymore that all the like, I guess training examples are acting independently of each other, or like they're not influenced by each other. It'd be interesting to see, but just even simple label propagation, how does that affect like the demographic parity? Okay, well, thank you everyone for coming.
Okay, great. Thank you.